Okay, so now we're going to do some example problems from section 2.5. So the first thing is we're going to be asked to find all the complex roots of this. Now, this being a quadratic. So this is actually pretty straightforward. This is a lot like what we talked about last time around, which means, and we're going to write this in fully factored form, the x is going to be opposite b over 2 times a plus or minus b squared minus 4 times a times c, which you can probably see is going to be negative, right, over 2 times 1. So we get negative 5, 10 divided by 2, plus or minus negative 10 divided by 2, 100 minus, well, 4 times 23 is 115 over 2. So we're going to get negative 5 plus or minus the square root of negative 15 over 2. So I'm just going to keep this as negative 5 plus or minus root 15 over 2i. So those are the two roots. Remember, these come in pairs, which means that the factored form of the fully factored form of g of x would be, that's not going to be enough space. We'll put it down here. So the fully factored form of g of x, our final answer, will be x minus, well, negative 5 plus root 15 over 2i, and then x minus, it's always minus whatever the root is, right? Negative 5 minus root 15 over 2i. And you are welcome to leave it like that. That would be the final factored form. Okay? So in this next one, what we're going to try to do is figure out what the fully factored form of this one is. And it's going to be a little bit more complicated because it's cubic. So we know that it's going to have at least one real root. We talked about that in the example there, or the fundamental theorem of algebra video, and that it's going to have to cross the axis. So it turns out that one of the roots is 2/3. How do I know this? Well, A, I have an answer key, but B, you could factor this, right? So it turns out, or sorry, not factor this, but you could, well, there's a couple different ways to go. You could figure out all the possible rational roots, all the factors of 50 and all the factors of 3, and you divide them, right? And it gives you some possibilities. Or what you could do is graph it, and you'll discover it's like 2.6 repeating, so aka 2/3. So that being said, once I get one root in here, right, what I'm going to do is then do a polynomial division by 2/3. And in fact, I'm going to do a synthetic division because this is just a factor. So that means one of my factors is, right, is going to be x minus 2/3. Now, as a matter of fact, it's probably actually going to be 3x minus 2, which you'll discover is the same thing. And the reason that works is because we have this 3 here. Okay, but that being said, then we divide this out and we'll get a quadratic because it will theoretically should have no remainder if this is all right with the world. So if I bring the 3 down, I multiply. 2/3 times 3, the 3's cancel, is 2. 2 plus negative 2 is 0. Ooh, this is convenient. 2/3 times 0 is 0. 75 plus 0 is this. Now, what is 75 times 2/3? Well, there's two ways to go. 2 times 75 is 150, divided by 3 is 50. Or 75 divided by 3 is 25, times 2 is still 50. So that wasn't as bad as we thought. That means that the resultant is 3x squared, right? So we've got x minus 2/3 times 3x squared plus 75 is what this equals, yes? Now, what does that mean? We can take 3x squared plus 75. We can find out what its roots are. Because remember, we want to have 3 factors that we're going to end up with for g of x. I suspect some of these are going to be complex. Now, if we solve this, oh wait, I know they're going to be complex, right? If we solve this, what do? We subtract 75, we divide by 3, So we get x squared equals negative 25, which x is plus or minus. The square root of 25 is 5, but it's negative, so it's plus or minus 5i, which means our factors are x minus 5i, x plus 5i, and that would be the fully factored form. Okay? Now, under normal circumstances, we'd multiply this through, so we'd have 3x minus 2, but this will work also. Okay? So the fully correct factored form would actually be 3x minus 2, x minus 5i, x plus 5i, because then if you were to distribute it, you'd discover that, hey, that works. Okay? Now, if for justification, this is when this thing equals 0, right? So you could multiply through by the 3, and you just affect this one to make it so it's not a fraction. Okay? That would be the fully factored form. Okay, in number 36, you're doing much the same thing. So does it help to have a couple of roots to actually divide by? Well, turns out if you graph this thing actually, and this is where I'd recommend graphing it because that's going to be the easiest way to go, because what you need to do is find what the roots are. And when you find what the roots are, the real number roots, because they're going to, hopefully there's at least one. If not, then it's going to be a lot of guesswork. Now, it turns out they've done something nice to you for a change, and it turns out that this graph actually has a root of multiplicity 2 at negative 3. So at negative 3, this thing bounces, and it probably goes off like that, right? But because that is a root at negative 3 that has a multiplicity 2, remember multiplicities, right? That means that there's a factor that's x plus 3, and there's another factor that's also x plus 3. In other words, that root's happening twice. So what that means for our purposes is we can divide this out. That is, use synthetic division. It's a negative 3. That's why I use negative 3, right? Which is 3, which is negative 9, which is 1, which is negative 3, which is 3, which is negative 9, which is, hey, that just proves it's a root because the remainder is 0. So now what we can do is we can do another synthetic division with negative 3. To find the complex roots, because you look, this only has these two repeated here, right? And then there's, well, who knows where the heck the other ones are, right? Well, they're imaginary, is to get this down to a quadratic. Right now, this is a cubic, cubed, squared, x, constant, right? So then we just keep going. Which means that, and they've been really nice to us, haven't they? That is x squared plus 1 is the result. So we know that when we pull out one x plus 3 and another x plus 3, the last thing we get is x squared plus 1. Now that's not fully factored as linear factors, so we need to figure out when x squared plus 1 equals 0. Square root of negative 1 is I. So it turns out our fully factored, strictly linear factors, right? This is not linear because it has a squared, right? It's a quadratic factor. And I'm not going to run through the verification, which you don't have to either. But this would be, well, the roots would be negative 3 repeated twice, right? I and negative I. If you just said negative 3i and negative I would be okay. Please note these are indeed conjugates, but that is how you do this. Easiest way, graphically figure out a root that you can then divide out. In this case, we had to divide it out twice. Okay, finding a polynomial with given zeros. This is fun. Find a polynomial with real coefficients that has the given zeros. There are many correct answers. Okay, so we have 3, 4i, and negative 4i. So that means one of the factors is x minus 3. The other factor is, now here's a check. Are 4i and negative 4i conjugates? And the answer is yes, they are conjugates. So x minus 4i and x plus 4i. Where it's always x minus whatever the root is. Okay. Can you figure out what the cubic model is going to be? Well, sure, you distribute. My advice is to distribute this portion first, because you know that these are conjugates, right? So what's going to happen is you get x squared, x times x. You're going to get a plus 4i times x and a minus 4i times x, which are ultimately going to cancel, right? The imaginary parts will go away. That's the nice thing about this. And you're going to get a negative 4 times a positive 4, negative 16i squared. So that's x minus 3 times, well, watch, x squared minus 16i squared is the same as plus 16. Now we can distribute that. I'm going to do this a little bit strategically. So x squared times x is x cubed minus 3x squared, right? And then I'm going to take and multiply by the 16. So it's going to be plus 16x, right? And then minus, that's going to be 16 times 3, or 48. So that is our function, or one possible function, right? What are the other possibilities? So there are many correct answers. Well, could you multiply everything here through by some? So could you have some function a times f of x, that is some vertical stretch? Yeah, that would still have the same roots. So could you multiply here everything through by 2, and would that give you the same roots for this particular polynomial? And the answer is yes. So you could say 2x cubed minus 6x squared plus 32x minus 96. Remember, you had to multiply everything by whatever that value is. Okay, finding a polynomial with a given zeros. A polynomial f has real coefficients of given degree 4, so x to the 4th. It's got these zeros. Unfortunately, they only list 3, but that's not going to be that. And then it gives a solution a point. Okay, write it in completely factored form and then in polynomial form. All right, brace yourselves. Okay, the zeros. Here's 1, 2, 3. Oh, wait, we know the other 0. This is a complex root, so it occurs in pairs, as is the conjugate. So now we have our 4 roots. We have x minus 1, x plus 4, x minus root 3i, and x plus root 3i. Now, it turns out that there is some sort of vertical stretch that is unknown for this. Let's call it f of x, right? Such that it hits this solution point. So here's the deal. There are a bunch of infinite number of polynomials that are quartic that have these roots. There's only one that actually crosses through this point. Remember, this solution point is actually the point 0, negative 6, right? X, y. So what we're going to do is we're going to take this and plug in the information that we know, that is 0 in for x and negative 6 in for y, and then that'll enable us to solve for a, because that'll be the only variable left. Now, 0, I'll write it out to be generous. 0 minus root 3i and 0 plus root 3i, right? So what does that mean? Negative 6 equals a times, well, that's a negative 1 times a positive 4 times negative root 3i times a positive root 3i. Now this may look awful, but it's actually not. What is negative root 3i times root 3? Well, positive, it's going to be negative. Root 3 times root 3 is 3, so it's going to be a negative 3i squared, right? But what is negative 3i squared? That's really just positive 3, right? So we have negative 6 equals, and I'm showing a lot of work for this. I mean, you could skip some of these steps, of course. But that means that negative 6 equals negative 1 times 4 times 3 is negative 12a. Now, prepare to be mildly disappointed. This means when I divide by negative 12, I'm going to get 1/2. That's what the value of a is. Okay. Now, back to the drawing board. That means that the constrained polynomial f of x is going to be, instead of a being unknown, it's now we know it's 1/2, x minus 1, x plus 4, x minus root 3i, and x plus root 3i. Now, unfortunately, they want to also write this in polynomial form, which means we need to distribute this. Now, I'm going to hold off on the 1/2 and do that at the very end. Otherwise, I'm going to do this very similarly. I'm not going to spend a lot of time. X times x is going to be x squared Plus 4x minus x is going to be plus 3x. Negative times positive is minus 4. Let's clean this up a little bit. That's actually just an x, no I or anything. Now, x times x, we know to be x squared. These are conjugates, so we know that the I terms are going to cancel. Positive times a negative is going to be negative. Root 3 times root 3 is 3. But it's going to be negative 3i squared, so it's going to be plus 3. If you go through and distribute this, honest, it does work out that way. So we're going to get 1/2 x to the 4th plus 3x cubed minus 4x squared, now the 3, plus 3x squared plus 9x minus 12. So we're going to get 1/2 of all of x to the 4th minus x, 6 minus 4, oh, my bad. We got plus 3x cubed, pays attention to that, right? Minus 4 plus 3 minus x squared plus 9x minus 12. And you guessed it, we had to distribute now, so f of x in the end is 1/2 x to the 4th plus 3/2 x cubed minus 1/2 x squared plus 9/2 x minus 6. Okay, so there's our factored form. That's factored, right? And here is our polynomial form. Okay, and that is it for section 2.5 example.